So since we're going to be doing statistical thermodynamics first in the course, I wanted to give a mini lecture on probability, just so that you can understand some of the vocabulary related to probability. And so there's different types of probability. There's logical probability, and under logical, we have this rational degree of belief in the event relative to some evidence. And we use this in forensics a lot, but we also use it in making decisions. We use this to determine if the milk is still good, right? We sniff it. That's our evidence. Does it have an off smell? No, it's okay. So I have a rational degree of belief that the milk is good if I test it and then look at the evidence, okay? Now we could get more numerical about it, and we could get into empirical probabilities. I could test things. And this is where we like to go in science. We have a mathematical description of the measurable parameters, and we can determine numerically what the probability is. And this is where we want to get to in our quantum mechanics, statistical thermodynamics. We want to get to this empirical probability. It requires the foundation, though, of logical probability. In other words, the logical part is if it's close to 1, it's a sure thing. If it's close to 0, it's not a good bet. Okay, so that's the logical, rational evaluation of what the number means. So we can't have empirical probability without the foundation of logic. And then we get to subjective probabilities. So this is an individual degree of belief. And this is why people play the lottery, right? So they think, well, I know it's not probable that I'll win the lottery, but a $2 lottery ticket or maybe even a $5 lottery ticket is not a big expenditure, so they'll take a chance. So they have an individual degree of belief that it's worth my $5 for the minuscule chance. And you can have your individual belief that that's not a good thing. Others will believe that it is a good thing. And so then we get into this subjective. And what does it mean by subject? Well, we are the individual, we're the subject. So it's what we call mind dependent. So my mind will make a different rational or different degree of belief as to whether that's a good bet or not. Okay. Now this is also how we make decisions typically. So we'll take the logical part, but then we'll apply our individual biases and so on to whether an empirical probability is good enough or not. So, now this probability, or P of E, probability of some event, is the number of favorable events divided by the total number of events possible. So this is getting into the empirical side of things, and we can put measurements on those. So we could have a number of systems in the denominator, and we would have the system or configuration we want in the numerator, and we could calculate the probability for that happening. Now, there's some requirements. So for you not to be misled, each event must be equiprobable, and that's hard to prove, okay? So equiprobable events, like you can think about all of the strange things they do with the counting of the Powerball or whatever. When they pull the walls out, they have the ball, it's rattling around. They're trying to make it equiprobable. Okay, if they just had the balls all in the bottom and they reached in to grab the top, it's not equiprobable because the one on the bottom is not going to get chosen. Sometimes they dig around, if you're playing bingo and they dig around in there or trying to pull a raffle ticket. That's what they're trying to do, is trying to make it equiprobable. But you go in and you fold yours and they feel it and they're like, oh, there's a folded one. I'm going to pull that out. Maybe you've changed the probability in your favor. It's not equiprobable. And so this is a big part of probability theory, is determining if the situation is equiprobable. And so we really can't prove that they're equiprobable. So we say there's insufficient reason to be afraid of that they're not. And so we'll just set them equal unless there's a reason to not. And so that's the principle of insufficient reason. Probabilities of two events will be equal unless there's insufficient reason to believe they'll be different. And so you assume the dice aren't loaded. But if you roll a few times, like 1,000, and it comes up to not be the Gaussian distribution of events, then you're like, okay, now I have sufficient reason to suspect that they're loaded. But you have to do an experiment typically to rule this out. Now, there are some problems with empirical probabilities, that they're descriptive. So descriptive statistics are not predictive, but we use them in a predictive manner. So how can I take the descriptive statistics of any situation. Let's say life expectancy, okay, for males in the United States, let's say 74 years, okay. That's the descriptive statistic, okay. But what does that mean to me as an individual? Not really anything. It's not going to predict that I'll die at 75. It's describing the population, but it's not predictive, okay. Now, when they say all things being equal, that's the word they're kind of saying, the equal probable thing. There's an equal probable chance that I'll die before or after 74, but that would be the mean life expectancy. So large sample sizes, like the whole population of the country, that would give you a confident description, but large sample sizes are expensive. And so in chemistry, we would love to do large comprehensive studies, but it costs money. And so we've got to figure out a way to balance cost with the results that we want. And then descriptive statistics show correlation, that there's a trend, similar trends or dissimilar trends mathematically, but it does not show causation. You actually have to have a knowledge of the system and how event 1 is connected to event 2 to determine causation. And so this is why we say descriptive statistics are not explanatory. They don't describe why my life expectancy might be 74. Okay, you have to get into medicine and diet and exercise and all of these things as to why my life expectancy should be a certain thing. They just describe what it is, not what it ought to be or why it is. Okay. And let's look at some funny examples here. So this is one of my favorite web pages, tylervegan.com. What's the guy's name there? Tyler Vegan. Have y'all ever seen this before? Anybody? Good. Okay. So he went through and just downloaded tons of data from places like this. This is the Office of Management and Budget and the Center for Disease Control and Prevention. And he pulls their data down, and he has a software program that looks for correlations between random sets of data. And this is one of the ones. So he's correlating U.S. spending on science, space, and technology, and suicides by hanging, strangulation, and suffocation. And look at the trend. They correlate. They correlate with the value of 99.79%. They have that same trend. Isn't that crazy? And so this is statistics showing correlation, but it's not showing causation. I don't think spending on space causes people to commit suicide, you know. And so this is a great example of correlation is not causation. Yeah. So there's lots of these on his website. There are some hilarious ones. Okay, here's a couple more. iPhone sales and people who died by falling down the stairs. Okay. Now maybe they might be a cause there, but you don't know that from the graph, right? And so you could what could you do? You could, survey all iPhone users and say, do you live near stairs? Right? Like you have to study the system to figure out, is there actually a mode that would cause one to, create causation between iPhone sales and stair deaths? Okay. But still, it's a pretty big correlation, 99.4. This one is really weird too. This is a negative correlation. Okay. So as the works of visual art that are copyrighted in the United States go up, fewer females in New York slip or trip to their death. Again, negative 94% correlation. So what should we do to protect the females in New York? Yeah, so let's see, as it goes up, fewer fall down. So we need more art in New York. And, again, that would be a wrong decision because we haven't established that there's a causal effect. They're just correlated. And so it could just be, it's hard to believe it's random, but it is. It's just two different data sets. You put them in there and they go up and down in opposite trends, and it's a 94% correlation. So it's really hard for us as scientists to see things that are correlated and not believe that one causes the other. So, but it does make you want to go dig into it and see if there might be a causal link. And medicine is really hard with this. That's why they keep flipping, like eggs are bad, eggs are good. They'll see a correlation and they'll say, maybe this is something that causes heart disease or something like that. So that's why medicine in particular flips all the time and it gets confusing. So with that, we'll get into applying probability to chemistry.